Alright, good morning everyone. This is 9 o'clock now. Oh, it's almost 9. So this is the fall 2019 midterm 2 that they took last semester. And yeah, let's get started on this. So the very first question is, what are the UDP header fields in their respective sizes? Again, each UDP header field is 16 bits or 2 bytes long, and they are the source destination port numbers, the total length, and the checksum. This is a typo actually. Let's just say part B. The second part is name one good reason for application protocols to use UDP. Really, it just boils down to UDP is fast. It's fast, unreliable, and connectionless. And so what reuses are there is if you're just sending small amount of data, or you're sending a large amount of data that don't require consistent lifetime feeds. And what I mean by that is if you're using small amounts of data that you don't care if it gets lost or not, or if you're using large amount of data like in live streaming, then UDP is a fine choice because it's fast, low overhead, and if something gets lost, well, it's fine, just resend it or use the subsequent UDP packets to overwrite what was missing. Alright, so in question 2, this is a similar ladder diagram problem. Alright, so we have an ISN, or initial sequence number, of 10, and then for the server it's a ISN of 40. So here we have a SYN packet again, sequence of 10 obviously is described here, acknowledgement 0, length of 0, and so here we have a SYN ACK, and so a sequence of 40, an ACK of an 11. Again, as I've explained before, when you use SYN and FIN, we must have that increase by 1, or as some people call it, a phantom bit, because otherwise we'd get stuck in an infinite loop, and nobody wants to be stuck in an infinite loop. And so this follows the general trend of just 10, 11, because we need the 11 here, 40 is the 40 over here, and then 41 because of this SYN right here. And so now we can send data. So this sends 10 bytes of data, and this packet type you can leave empty, or you could put acknowledgement here. But so now you have an 11 because of this SYN right here, acknowledging 41 because of this SYN right here, and then a length of 10. Again, this length, or this data or byte, whatever is put here, is just referring to the payload that you're sending. And so now we do a 11 plus 10 to get this acknowledgement of a 21. This is an acknowledgement of 41, so the sequence number must be 41. The server is sending 5 bytes of data, so the length is 5 here. And then he receives it and the disconnect occurs. Now I've described it before, but right here, this right here is now actually incorrect. This needs an acknowledgement here. This is because this is actually sending data, so this must be a FIN ACK right here. And because this is a FIN ACK, this guy can then send just a FIN or a FIN ACK as well, or simply an ACK, because it would be acknowledging both that I received something and I'm acknowledging the disconnect. But in this case, ignoring that this is incorrect, imagine this was a FIN ACK, then the sequence is indeed 21 as described here. The ACK must be indeed be 46, because 41 plus 5 is 46, and we're sending no data, so the subsequent packet should be as well 22 because of the FIN, with a sequence of 46 for here. And the acknowledgement is then indeed correct because we are getting there's no data being sent, but we do need to increase the acknowledgement because of this FIN here. But again, this right here is incorrect because we need an acknowledgement beforehand if we are following this three-way close, because there is data being sent right here. So that is wrong on my part. Alright, briefly describe TCP flow control mechanisms, who is doing what to whom and how. So the receiver controls the flow control. It does so by advertising the receiving window size in its header, and that header field obviously gets passed through the acknowledgements to the sender, and that will let the sender know how much data is left inside the receiver's buffer. And so in TCP congestion control, it is the sender who controls it, and it does so by timing the number of ACKs through the RTT times. So if there are any loss events because of timeouts or multiple triple duplicate acts or something similar that occurs, it knows that there are issues within the network, and depending on what protocol or congestion avoidance protocol it has, it will adjust accordingly. So which statements are true regarding DHCP? It is a application layer protocol. I think I described this in the review video. Hopefully I did. And then it uses well-known ports. It does not do public-private IP conversion in its default configuration. It is potentially possible if you are a server administrator to set it up in such a way for something similar to be set up, but by default it does not do that. And then arguably the ipconfig utility does use DHCP, but in reality it does not explicitly use it. Now when you use ipconfig, you can request and flush your DNS and change your IP or force it to change. If you don't want to turn off your router, that's technically true. The method of doing that will not be described in this video, but typically for almost all general use cases, ipconfig does not use DHCP. Okay, here's an advantage and disadvantage of NAT for question 6. Advantages is it acts like a firewall, more devices are on the network, etc. Those are all like potential reasons. Disadvantage, there's more overhead, device IP masked behind the NAT, which prevents direct connections, and anything else that you can come up with. There's a lot of stuff, so I didn't write them down all here. So this is actually apparently one of the harder parts, or one of the harder questions on this exam, at least for the people that took it. So part A was, what is the subnet mask for this network? And this is the network right here. So as you can see, I gave you an entire address, and if we just look at this, we have /26, right? If we have /26, then we know that just 32 minus 26, right, is going to equal 6. So we know then that starting from the right side this time, the first 6 bits starting from the right going to the left are all zeros, because in an IPv4 address there are only 32 bits. This is the way I rationalize out when I'm trying to do it like this. So everything else is all ones. So that means that this is 255.255. And the very last one must then be a 192, because right here this is going to be, if you didn't know, 128 plus a 64. These two right here, that's what that indicates, which gives us 192. So part B now is, suppose we want to create 4 subnets from this block, with each block having the same number of IP addresses. What are the prefixes of form A, B, C, D, that's whatever, for the 4 subnets? Alrighty, so this comes down to if you understand how subnetting works. If you don't remember, subnetting and supernetting are just simply methods of ensuring you can, in your own private or rather local network, you can assign, you can split off and assign each of your connected hosts a unique IP address. This is of course assuming that you own this entire range, but let's not get into the actual technicality of the truth behind it. So let me just copy that real quick. We have /26 there. We want to create 4 subnets. Since we want to make 4 subnets, right, What is 4? Well, we just do 2 to the power of 2, and that gives us 4. So that means that to create the subnet, we must take 2 of the um, 2 of the host ID, or 2 of the host bits, and no, it's 2, yeah, 2 of the host bits, and take them and tack them on to the right here onto the into the mask host bits. What was it? The host bits? No, it's the yeah, you're taking away 2 of the host bits. I apologize. And so what does that do for you? Well, the moment you've got that, everything splits up evenly. As you can see, you just get, if you want it, you could just do the math behind it as well, to 32 minus 28, which will give you 4, right? So now you're just working through the power of 4, which is just adding 16 each time, right? So 2 to the power of 4, which gives you 16. So now you just add 16, and that's going to be 80, and that's going to be 96. It's going to be 112, or 112. The reason for this is because this is saying that 64 through 79 are this this sub network host range, and if you count it up, you will get 0 to 15, which is basically what this is here, and then yeah, that's basically what you get. This should actually be a -1 to get 15 because of the preserved host. And so if you just add this number straight up, you will get it correct, but this gives you the number of actual hosts you can use. Oh, actually this should be a 2. I'm sorry. Because you have 2 reserved hosts. And that's basically that. So basically you could just if a similar question is asked, you could just do all of this. Note again, the reason why I got this is because this was originally 6, right? I want to create 4 subnets, and to get 4 subnets from this, I need to take away, I need to create more networks. And to get more network bits, I need to take away host bits. And as we know, as explained here, we're working in binary when working in bits, so we go 2 to the 2 to get 4, because it's 4 subnets. And so we take away 2 of the host bits to get /28. And once we get that, we can split it off evenly to find it out. And it's going to be even if there's another question like this, because again, I do the math behind this. And so to the 4, and then I get 16 hosts total for each subnet, and you just tack it on, just keep adding them over, and that's what you get. So again, this question is actually fairly straightforward if you know what subnetting is, how to do it. But for some people it might be a bit confusing. If you have any questions, please feel free to email and all that jazz. Okay, so 8. Circle all answers. Only complete answers get points. What statements are true regarding ICMP packets? 1. They acknowledge recipient of a fragment. That is false. ICMP, hopefully as Frank described it, is just a diagnostic tool for pretty much the network, or for hosts to diagnose the network. B. They guarantee datagram delivery. Again, false. ICMP has nothing to do with datagram delivery. In addition, datagram is the term used for UDP. So it has, I don't even know why someone would circle that. I know in this class we used analogous. No. We use the term datagram and packets the same, especially when referring to different layers, but when working in the actual industry, the technical terms would be datagram segments in the transport layer, packets in the network layer, frames in the link layer, and just data in the application layer. But yeah, but if you don't want to get all technical about that, just know that, well, like ICMP also cannot do anything with datagram delivery because it's not a it's not in the delivery, it's not a delivery protocol at all. It has nothing to do with it. C, they can provide hosts with information about network problems. Yes, again, ICMP is for diagnosing the network. D, they are encapsulated within IP datagrams. Yes, again, well, this should say packets, but you know, again, in this class we're using it I can't pronounce the word. I know what the word is. I can't pronounce it. I'm sorry, everyone. We're using the words synonymously. So here, yes, that's true. You encapsulate a datagram inside. I mean, you encapsulate an ICMP header within an IP packet. Okay. D, explain step by step how pinggoogle.com works in detail. Packet level. So the way I wrote in here, CLI/terminal application gets the ping to google.com and passes down requests to network driver. The transport protocol isn't too important because a raw socket can be opened directly, to contact the network layer. And the network layer IP packet encapsulates the ICMP packet, which has the ping request message. Once Google gets the ICMP packet to send it back, its own IP packet, encapsulating its own ICMP packet with a ping reply, which is this is pretty much it. It's a bit technical. There could be a few more things added to it, but if you can explain pretty much just understanding that it goes down to the network layer and into an IP, an ICMP packet and header gets formed and gets encapsulated. That's pretty much what I was looking for. You didn't need to know about raw sockets or anything about that, but that would be a more complete answer. And here we go, finally, a very beautiful topography. I think, oh, the last question was yeah, that was that. So here we have, what was this? This is a link state algorithm. As you can see, it's Dijkstra's shortest path algorithm, so it's link state. Now remember that distributed Bellman-Ford is the distance vector algorithm. So this is the way that I would show the steps on how I get my link state table, or to find the shortest path, and then again to create a routing table, I will have the interfaces somewhere listed, and you would just have to map that. And to see how that is done, let's just delete all of that real quick. And at the side, you would have again like interface right there, and then this is referring to the interface you want to reach. This is from or send to, the interface you need to send to, and then this is the cost associated with it. And so again, so if we're at node T and we want to go to interface U, right? So let's say it's interface U. Right now I don't have values in there, but we send to, well, we simply, or rather this should be sent from. So send that from T, right? And then the cost here is 2, as we can see there. And then interface, let's say V. Again, this is going to be likely to from T, so right there, and then it's a cost of 4. And we can see that here, that is true, from T to U, and then V is the next one. So let's do W next, because I'm just going to follow this now to make things simpler on U and I. So W, which is all the way over here, it comes from U, as we can see right there. So it's a cost of 5. So we sent it from U. Obviously, this means we're sending it from T to U to W. I hope you understand how that worked out. And then for y would be next, let's just hurry up and just write x and z. And just do it like that. Like that. Oops. And so from y, we are going from, this is y, and we're coming from t. So that's how I would do that. And the cost associated with it is a 7. And x right there, that's a 7 from v. And that is the cost associated with that. And z is the final thing, so that's 15. And we have an x there. That 15, and that's the x. Sorry about that. And that's basically what a routing table would look like. You have the interface, which interfacing you're sending it to, or sent from. You should say send. Yeah, sent from. Or you could do send to. Send to might be a better way of phrasing that. So we are sending this directly to you, right? And so W is getting it from, we are also sending to you there. To Y, we send directly to Y, because we are directly connected. From X, we are going through V, if I recall correctly. Yes, so we should be sending from V. And for Z, we should be sending to V as well, because we are going through X. And then from X through V, because we are going 4 plus 3, so that's 7 plus 8, that's 15, to Z. And that's the routing table right there. It's fairly straightforward, very easy. Usually these are 4-point questions, and the routing table, I would say, is your 1 or 2 points, depending on what I'm asking for. So please do the routing table as such. And it's not hard either, as you can see. You just have to do an additional table. But do note that this is the link state algorithm table being shown here. In the distance vector table, you need to do an individual table for each node first, and then a final table that combines all of them for the shortest path. And then you need to do a routing table that shows exactly like this. This is the final one that I can find. My 2018 one, I think I had a distance vector. Yeah, but the routing table is still the same. So we are sending it sent to from T. Let's say that. That way it's more clear for everyone. Yeah. And this would be the most, like, that's 100% clarity. I know what you're saying. I know everything what you're trying to describe. I can quickly look through your own work right here to make sure it matches up what your cost is right there. So this perfect point, this is what I'm looking for. Please do it something at least like this, if not very similar. Alright, and so the last question right here is the fragmentation question. I think this one would be the one that's gonna trip up most people. Yeah, I think this is gonna be something that's gonna trip up the most people the most, and really, what you should be doing first is just work it step by step. So I'm gonna delete all this real quick, and again, the first thing you should check out is find out how many packets you need. Alright, how many packets do I need to send? Well, I see right here it says station A needs to send 2,480 bytes worth of data, right? And that we have a payload, we have header of 20 bytes, and the MTU is 1820. So if we just do 2480, right? And then give me that calculator. Actually, just do the calculator. 2480 divided by 1820, or because I'm not including the header, I removed 20 bytes there. I am looking at approximately 1.37 complete fragments, right? So what on earth does that mean? Well, as you can see here, there's a second fragment. There's a second MTU, or a second interface, where fragmentation is going to be needed. So the first fragment, we expect at least one to be complete with a payload of 1800, and then the second one to have an incomplete payload, right? And this is what you see right here. So fragment 1 has a data length, or a payload, of 1800, right? And please don't get confused of what data length is. This is not total length. If I ask for total length, then it would be 1820. But as always, I ask for data length because I want to see if you can, tell me how much payload data is inside your packet. It's very simple and it's the easiest thing to miss. So please do not put total length. Alright, so we are expecting approximately 1.37 frags. And that's pretty much what we have here. We have a complete fragment and a secondary fragment. So you roughly know that your first set is correct. And then we can go on. So 1800, because 20 bytes within this MTU will be reserved for the header, is going to be divided by 8, which gives us 255. So the offset, so your offset is equal to 255, or no, 225, I'm sorry, for 1800, right? So that's for the first one. Okay, now that means that we'll have a fragment offset for the first fragment of 0, and for the second fragment starting at 225. Now remember, this is saying bytes 0 to 224 belong to fragment 1. And then fragment 2 has byte 225 onto whatever this divides out to be, which doesn't actually matter because there are no subsequent packet until we hit the second MTU. So the moment we hit this second MTU, oh wait, before that, please set the correct flags. As you can see, fragment 1 has one more fragment following it if we ignore these right here the way I wrote it, and that's why this is 1, that's 0. Okay, now continuing onward. Now we hit the second MTU, this interface. Now we need to cut this down, our first fragment, because we have a payload of 1800 and we have a total length of 1820. So to get to this split, well, because we know that 1800 is just divided by 3, or you just need to multiply 600 by 3 to get to 1800. It's very easy to find out the total data length for each fragment right here. Oops. And so now all we need to do is just calculate the offsets. So do 600 divided by 8. So 75. So 0 to 74, 75 to 149, and then 150 to 224. Now as you notice here, the fragment offsets are still within the range, right, of the original packet. And so if you have a weird fragment offset that's like with going outside this boundary right here, you know you did something wrong. So as you notice, the very first fragment offset again though is still 0. So just keep note of that, and that's just going to be another secondary check to help you make sure that your math is correct. Alright, but then all of these also inherit the more flag being set. That's because, again, this is the first fragment. Even though it got fragmented multiple times, it's still part of that first fragment, which is everything before the second fragment, which inherited, or which has the 0 more flag set. So when we get to the second set, again, because it's 680 bytes worth of data, we just need to split it to 680. Now this obviously is going to, this obviously maintains the fragment offset of 75. So this means that it goes from 225 to 299. But as you notice here, even though the original is a more flag set to 0, the very first fragment is set to 1. Again, this is because we are splitting up the data sequentially. Because there is more data coming after this fragment, we must, when we are splitting up the fragment even further, simply set the last fragment to 0, the more flag bit. So, however that occurs, software side is up to the developer, but the way I would do it, as I answered a previous student before, and I apologize for the miscommunication then again, is that you're simply looking for the last fragment when you have this flag set to 0. Because if you must fragment it again, that means that up until you reach the last fragment, everything is just going to be set 1. If you understand what I'm saying. If not, just make sure that you have the correct flag set, and that's basically it for this exam. I personally think that this was a fairly easy exam, and that it was doable within probably 30 minutes or 40 minutes. Definitely I could do this within 20 minutes if I'm checking my answers 20 to 30 minutes if I'm checking my answers constantly. But it's not really hard, it's just very long. If you're following what I'm telling you to do, just work through it at a decent pace. And yeah, a lot of this stuff that we've already explained in class. If you feel confident in yourself and you listen to what I'm trying to explain here, like things that people constantly get tripped up on, and make sure you don't catch yourself tripping up on it, I think you're going to do really well on this exam. That's it for this video lecture. Not video lecture, I mean a review. If I have time, I will try to find the other midterm 2s from 2018. But this is it for right now. The next videos are going to actually be the lecture, me covering the lecture content for after midterm 2, and also the final review videos as well. And I will see you later then. Hope everyone has a successful midterm 2.